So we're looking at a case of velocity of center of mass in the absence of external force. So first thing is, we know that the external force influences the center of mass in this manner, right? So here you have external is your net external force, m total mass of the system, and ACM your acceleration of center of mass. Now, since we are talking about velocity of center of mass in the absence of external force, right? For the external force being equated to 0 Newton, we have mass times of acceleration of center of mass is equal to 0. And so this and this can cancel, right? Mass cannot be 0. So therefore, this has to be 0. Now, for that to be 0 means what? From here, it implies the velocity is constant. So basically, if I have an object moving in any manner, right? Some object can be, this you might not realize as of now, but we have objects which are, there was one cigar. You guys can web search this. There was a cigar structured object that went, I think, around the sun, and it took a elliptical path and stuff like that. So initially they thought it was a alien probe and stuff like this, and the shape was weird, and there were quite a few things discussion. So that, I think it was going round and round also, if I don't remember exactly. So what I'm trying to tell is, if we have a structure going round and round, but there's no external force acting on it, the center of mass will follow a straight line. It'll be moving along a straight line. Okay, I'll try to show it with my video. Of course, there is a frictional force acting on it. So you guys can see the center of mass, right? So that's the center of mass. When I hit center of mass exactly, then it moved in a straight manner. So that's okay. I'm trying to show you guys this actually. Yeah, it's not exactly okay, not an ideal scenario because there is frictional force acting on it. But yeah, we'll make a separate video for that. So we need to set up few things. But point is, this will be moving with a constant velocity, even though things around it are rotating. If this being the center of mass, this will go in a straight line. Okay. So this very discussion, the conclusion is that in the absence of any external force, the center of mass of the system moves with a uniform velocity. So this reflects your Newton's second law. Again, this is much fun to learn and watch when you do it with experiments, So there are videos which will show this, but yeah, we'll have our own video as well. Next, momentum of center of mass in the absence of external force. So for that, let's consider a system of n particle each with its own mass m1 till mn, and velocity v1 till vn, and linear momentum p1 till pn. Now, in absence of external force, acting on the system, what we're looking at is F total will be equal to 0. So basically, the net force is 0, means all the forces when added in a vector form, in its vector form, will be equal to 0. But yeah, force is nothing but mass into velocity acceleration. And in turn, I can rewrite this as m1 dv1 by dt plus mn dvn by dt. All of this is equal to 0. And if you guys remember, and you should remember, the algebra of limits and derivatives, I can rewrite this entire expression in this manner. Basically, guys, if I differentiate this, what will I get? If I differentiate this expression, what will I get? This, is it not? Mass is constant, it will go out. And derivative of v1 plus so on and so forth. So I just did the opposite of it. Now, if we integrate both the sides, on integrating both sides, what do you end up with? This will disappear and you have m1 v1 plus mn vn. This entire thing is equal to a constant, right? And this is basically nothing but p1 plus pn, right? Mass into velocity is your momentum, and this constant will be the momentum of the center of mass. As a conclusion, the total momentum of system of object remains constant if there is no external force acting on it. This is a law of conservation of linear momentum. Again, all we are trying to tell over here is that whatever rule we learned in our previous classes, here too it holds good. That's all we are trying to prove. There's nothing fancy happening over here. We're just trying to tell the center of mass behaves like a point object that we considered to this point. Whatever was applicable to the point objects that we dealt with to this point, to this chapter, before this chapter, all that is followed over here as well. Nothing fancy is happening. Of course, when you do the experiment, there's quite a few fun things that we get to see. And this in action is quite brilliant to watch, honestly. But yeah, mathematically, this is it. And we'll be using this directly, indirectly. So we should know this.